Today's lesson is going to be on chapter 22, section 1, and it is a lesson in which we begin to talk about current flow. Previously, we have been talking about electricity in terms of static electricity. Static means standing still. Current flow means that electricity is on the move. As I said, current is electricity on the move. It's no longer standing still as it was in last chapter. So current, to get some definitions of it, current, and the symbol that we use for current is I. It is a measure of how much charge moves past a given point in 1 second. So if we had, say, a piece of wire, I'm going to try to draw a piece of wire here. And this was a conductor. You guys know what conductors are. And say we had some electrons in here that were moving along. So you know that electrons have charge. So it's a negative charge. And they are moving this way, right? We've got some coming in, we got some coming out. And if we were to just stop right here and say, okay, I am going to count how many electrons pass this point in 1 second, we would be measuring current, because by counting electrons, we are actually, there's a charge, there's an amount of charge associated with each electron. It is what, that 1.6 times 10 to the minus 19 coulombs. We can actually count the number of coulombs that are going by that point in 1 second, right? So that's what current flow is. That's a visualization, is it? Now, we have a way, the units for current is called an ampere. An ampere, that's kind of a funny name because it's this guy's last name, and he's got a funny name, Andre Marie Ampere, right? So a lot of times we just shorten it to amps and then abbreviate it as the letter A, okay? So 1 amp, as I said, is a rate of charge moving past a point in 1 second. So 1 amp is equal to 1 coulomb passing by in 1 second. It is, an amp is a coulombs per second, but nobody ever says coulombs per second. They just say, it's 20 amps, right? So if you were to go into the circuit breaker box in your house and open up the door and look at all the circuit breakers, right? So here's the circuit breaker board. Here's somewhere like behind the ironing board in your pantry or something like that. There is a door. And if you open that door up, then you will see a row of circuit breakers. Maybe there's 2 rows or something like that. If you look at each circuit breaker, there may be a number like 20 on it. And that stands for 20 amps. And that means that if for some reason you've got the crock pot and the George Foreman plugged into the same receptacle in your kitchen, then that 20 amp breaker is going to blow, because that's way too many coulombs passing by in 1 second, and that gets the wires really hot. The circuit breaker is designed to keep your house from burning down. So that's a real practical application of when we talk about amps. That's where you're going to see it in your home. And if you've ever had to flip a circuit breaker, you'll know what I'm talking about. All right, let's move on to power, because there are some practice problems that are related to power. So let's get those definitions down. Again, if you're watching this on a recording, then what you can do is stop the recording at any time so that you can catch up with your notes. Power now is something different. Power is the product of current and potential difference. So power, P, current we know is I, and potential difference, we have used the letter V before. Here I've written it delta V because that's what it says in your book, right? So when I say product, I literally mean the mathematical product of those two quantities. Power is equal to current times voltage. And in fact, most of the time we see that formula, we will use this formula. This is the formula. This is the boxed equation this is what you're going to get on a test. The delta V just means that, let's just say, let's go back to what we learned about in mechanics when we were talking about potential energy, okay? Say there's a cliff and it kind of looks like something like this, right? And we want to know, what is your potential energy relative to this point, right? Say you are 20 feet high, 20, well, feet, whose feet are we talking about? 20 meters, right? Say you're 20 meters high from the lake, but you're only 10 meters high above the cliff, right? So if I ask you what your gravitational potential energy is, it'd be your mass times the acceleration of gravity times the height. So if I ask you what your gravitational potential energy is, you would have to say, well, Mr. A, are you talking about what is my GPE relative from where my location is currently to the lake? Or are you talking about what my GPE is relative from the cliff here down to the beach? And so if I said from the cliff down to the beach, then you would use 10, right? Because this is the difference in the height, right? From where you're at now to where I want to measure from. So even though you're 20 meters above the lake, the difference between where you jump and where you land is only 10 meters, right? So that's where this delta comes in, right? Same thing applies to voltage. When we talked about capacitors, we didn't talk much about capacitors, but when we had a charged plate with positive charge on one side and negative charge on the other side, we were actually talking about the difference in voltage applied to each side of the plate. Okay, so that's where that delta V comes from. Okay, but in this chapter, when I give you a voltage, I'm not really talking about a delta V unless I specifically say the difference. You're just going to want to use it as a V. Okay, so that's what power is. It is the product of the current and the voltage. Power is measured in something that we call watts, and you've probably heard that term watts before, unless you did a biography on James Watt. That's who the W is capitalized because it's the guy's name is James Watt. You probably heard watts when you're talking about light bulb, right? So this is an old-timey light bulb now because now we have all kinds of different kinds of light bulbs. But this would be like a 60-watt light bulb that your mom would say, go into the pantry and get a 60-watt light bulb. And, well, we only have 120-watt light bulbs. Well, that's too bright for the lamp. I'm going to have to go to the store, right? So when we talk about watts, where you relate to that because you've had to go get light bulbs before, right? Let me put it a different way. Power is a rate of energy flow. Now, I want you to have in your mind now, imagine a big wide stream which is flowing with a certain amount of flow. It's a wide stream, so it's a wide stream, and so it's not moving very fast. And if somebody asked you to walk across the stream, you would say, well, hey, as long as it's not too deep, no problem. I can walk from one side to the other. All right. Given that certain amount of current flow, you're not too worried because the lay of the land is such that the water isn't moving very, very quickly. There's not a very steep fall in the river, and so it's just kind of moving along slowly. Now, a little further down the stream, there's a waterfall. Okay, now someone asks you, hey, why don't you walk from one side, you're standing at the base of the waterfalls. Why don't you walk from the base of that water from one side to the other side? you would have to think about that a little differently, because now it's not this, it's the same amount of current, but upstream of the waterfall where it's moving slowly, it's, oh, it's a nice little stream. Now, when you're down at the base of the fall, it's, I don't know if I want to do that, right? That's what power is. There's a lot of power at the base of the waterfall because the difference in the height is extreme, right? So now I hope I give you some kind of a gut feeling for what power is. Same amount of current flow, but when you change the steepness of the river, you're talking about increasing the power. I hope that makes sense to you, okay? Because you're going to get asked some questions, and it's always very helpful if you have some intuition, right? We measure power in watts. As I said, it is a rate of energy flow. So energy, you will again remember from mechanics, as we measure that in joules, and then this is joules per second. Okay, so that's what a watt is. All right, so make sure you got this in your notes. Again, you can stop the recording if you need to. That should give you a good idea of what our buddy old James Watt came up with, right? All right. So him and Mr. Ampere were contemporaries, right? They were doing the same kinds of things at the same time, and it all kind of came together. Okay, I want to just throw out one more set of definitions here, because your book, if you read it, they say, oh, and you have learned, and they skip right over this. Yes, you probably did learn it, but you probably forgot it already. So let's recap what energy is. It's the same concept we were talking about when we were talking in mechanics about energy. It is the potential to do work. So if you got if you just ate your sugar pops, and now you've got a bunch of energy, and you go push the chairs around the kitchen, you can actually get paid as a mover, right? Because you're actually doing some physical work with that energy that you got from your sugar pops, right? Energy is measured in joules. Joules. You'll remember that I just kind of made that funny noise for some weird reason. I always said that when I said joules. 1 joule is actually an SI base unit. It is 1 kilogram times 1 meter squared times 1 second squared. That, I think, comes from, let me think about this for a minute. Remember, so work is equal to force times distance. Force is measured in newtons, which is a kilogram meter per second squared. So if we force times distance is measured in meters. That's where they get the 1 kilogram meter squared second squared. So energy is the potential to do work. Energy and work are measured in the same units. They're measured in joules. And this is how you see that it is actually, those units are related. They are a standard base unit. Okay. All right. So here is your boxed equation for energy. It can be determined by the rate of energy flow, power, times the amount of time that energy is flowing. That's how much energy you're going to have, right? So if you're a big, powerful chair pusher arounder person, and you push, and so you're real powerful. So instead of $10 an hour, they give you $20 an hour. If you push around for an hour, then you would have had to have that much sugar pops energy in order to do that. I don't know. That's just a silly kind of analogy, but it works for some folks. Okay. Wait a minute. Wasn't there a guy named Watt? No, Joule. Yes, there's a guy named Joule. So James Prescott Joule. So we capitalized the J too, in honor of that famous physicist, Joule. Okay.